Unit 6, podcast number 3, reaction stoichiometry. Before I get started on this one, it's going to be really helpful for you to have your periodic table. And if you can find your old mole map, because the mole conversions will definitely be happening here. In the last two podcasts, we look at composition stoichiometry. We're looking at mass relationships within just one substance. With reaction stoichiometry, we're now going to be looking at the mass relationships between the reactants and products in a chemical reaction. Now, this is really all based on balanced chemical equations. So we're going to look at different ways we can interpret what exactly those coefficients mean. The coefficients in a chemical reaction can mean particles, they can mean moles, and if we're talking about gases, they can also mean volume. So if we look at this equation as an example, we've got that hydrogen and chlorine gas coming together to make HCl gas. The coefficients that are there, we can read it this way, filling in these blanks with really any of the different words that we need. You could read this as one particle of hydrogen and one particle of chlorine come together to give you two particles of HCl. Or if we want to deal with more than one molecule at a time, we could certainly say that 1 mole of hydrogen and 1 mole of chlorine come together to make 2 moles of HCl. Since these are all gases, we could also say that 1 liter of hydrogen and 1 liter of chlorine, when they combine, we're going to get 2 liters of that HCl. So those coefficients can mean particles, which would be individual atoms or molecules. They could mean moles, or they could mean volume in liters if we're talking about gases. So this ratio of coefficients is really important. That mole ratio is going to be a conversion factor that will relate the amounts in moles of any two substances in a chemical reaction. So a mole ratio really is looking at the coefficients in a balanced equation. Since most of the time we deal with large amounts of the substance, 1 molecule at a time is not terribly useful in dealing with chemical reactions. And we don't always have gases to work with. So for the most part, these coefficients we're going to be using as moles. If I look at this balanced chemical equation then, the mole ratios that are here are the coefficients. So if I want the mole ratio for aluminum oxide to aluminum, it's a 2 moles of aluminum oxide for every 4 moles of aluminum. So you could call that a 2 to 4 ratio, or to make it even simpler, we would call that a 1 to 2 ratio. You're going to get twice as much aluminum as you have aluminum oxide. If we were looking at aluminum to oxygen here, I would compare the coefficient for my aluminum to the coefficient for my oxygen. So that would be a 4 to 3 mole ratio. Now this is important because it's going to allow us to link the products and the reactants in calculations. This is sort of the bridge if I am doing some math converting between grams and moles with one substance and converting between grams and moles of a different substance. To bridge from one substance to another is going to be using this mole ratio. So let's take a look. Just practicing the mole ratio part. For your turn number 1, we're going to use this equation. I want to answer what's the mole ratio of hydrogen to ammonia. NH3 is ammonia, by the way. And then what's the mole ratio of ammonia to nitrogen. So take a moment, write down those mole ratios. For hydrogen to ammonia, we're going to compare your coefficient for the hydrogen to the coefficient for the ammonia. That'll give you a 3 to 2 mole ratio. If we're comparing the ammonia to the nitrogen, anytime you don't see a coefficient, you assume it's a 1. So that would be a 2 to 1 ratio. Now we're going to start attaching some real math to this. If I want to convert from moles of one substance to moles of another, this mole ratio is going to be my bridge between them. So for example, I've got lithium and oxygen reacting to form lithium oxide. I want to know how many moles of lithium oxide will form if I start with 2 moles of the lithium. So I'm going to be connecting one substance to another. First step is, for any of these kinds of problems, is always to write and balance the chemical equation. Sometimes that'll be done for you. Sometimes you'll have something like this where you've got to write the equation yourself. So I've got lithium and oxygen coming together to form the lithium oxide, balanced it to give me the same number of each element on both sides. Next, you're going to identify what it is you're starting with and what it is you're looking for. There's going to be a lot of numbers in these problems, so it's really important to have a clear idea of where you are starting and where you are ending. So in this problem, the only number I was provided was 2 moles of lithium. So that is my given. That's where I'm going to be starting a conversion. The unknown is what's the question asking for. It asks for how many moles of lithium oxide am I going to get. So moles of lithium oxide is my unknown. Now we're going to set up a one-step conversion problem. This is a dimensional analysis kind of thing, except my mole ratio is now the conversion factor. The mole ratio that I need is that relationship between the lithium oxide and the lithium. And these numbers then are what are going to get plugged into my conversion. The same process we did for any dimensional analysis problem, which means what you're getting rid of goes on the bottom and what you're looking for goes on the top. So this would be the way that I set it up. My given right here is what I started with, so that goes first. My mole ratio I put in an order that cancels out what I'm trying to get rid of and leaves me with the one thing that I'm looking for, which is lithium oxide. The numbers here, the numbers come from the mole ratio here. So if I start off with 2 moles of lithium, I'm going to put the 4 moles of lithium based on that coefficient, 4 moles of lithium on the bottom. That's what's going to make those cancel out. I'm trying to find lithium oxide. So we take that part of the mole ratio that came from lithium oxide and put that on the top. This cancels out moles of lithium. Multiply the top, divide the bottom, and I'm going to get 1 mole of lithium oxide from my 2 moles of lithium. And because the numbers here are fairly simple, that should kind of make sense. If I compare my mole ratio here, I have half as much lithium oxide as I do lithium. So if I started off with just 2 moles of this, I'm going to end up with just 1 mole of that. That's the basic idea. Now we'll see if you can try one. Got hydrogen peroxide, and here is the formula for that. Decomposes into water and oxygen gas. You want to know how many moles of oxygen will be produced if you start with 5 moles of the hydrogen peroxide. I'll help you out with the balance equation. The rest is up to you. Figure out what you're given, what your unknown is, set up that one-step conversion, and figure out how much oxygen you can get. Give it a try. Your given was the only number in the question. That was 5 moles of the hydrogen peroxide. So that's your starting place. The unknown is whatever the question was asking for. The question asked for how many moles of oxygen, so that becomes your unknown. Now we can start plugging in numbers. Your given is your starting point in the conversion, so that goes first. My actual conversion factor, I put what I'm trying to get rid of on the bottom. Number comes from the balanced equation. What I am looking for, which was moles of oxygen, that goes on the top. Number comes from the balanced equation. Multiply top numbers, divide bottom numbers, and I get the 2.5 moles of oxygen. So now we can take this and start sort of building off of our mole map and expanding it. Now, rather than having just a mole map for one substance, we can bridge from one substance to another. So if you think of just this piece here of your mole map, you have this already. To go from grams to moles, you can, if you're going from grams to moles, you're dividing by the molar mass. If you're going from moles to grams, you're multiplying by the molar mass. If I had some other random substance, same exact process. Now you've got a bridge in between 2 different substances. So now I could start you with grams of one thing. Grams of one thing. You could convert from grams to moles. Then, based on what we just did, you can go from moles of one substance to moles of another. And then I could go from moles of the new substance all the way to grams of the new substance. That's about as long as the problem would possibly get, is 3 steps like that. We'll start off with just 2 steps, going from grams to moles of something new, and then we'll try adding a 3rd step after that. Alright, so we're going to talk about the chemical reaction that actually powers an airbag. When sodium azide is activated in an airbag, nitrogen gas, that's what inflates the bag, and sodium are produced according to this equation. Kind of got cut off there. If half a mole of that sodium azide reacts, what mass of nitrogen would result? First step is always to get a balanced equation. So if your equation was not balanced, you've got to balance it first. If, by the way, I give you coefficients, you can assume they are correct. If I give you 0 coefficients, you have to check and make sure it's balanced. But I will never give you wrong coefficients. I just might not give you any. So we've got to balance the chemical equation here. Then we want to identify what our given and what our unknown is. The only number in the question was the half a mole of that sodium azide. So half a mole of the NaN3. What we're looking for is what mass of nitrogen would we get. So mass of nitrogen is our unknown. Then I can set up what is now a 2-step problem. My given, always the first thing I write down. That's where my conversion starts. This next piece is exactly what we did on the last slide. This is the mole ratio part. I'm trying to get rid of the NaN3, so that's what goes on the bottom. Number comes from the balanced equation. I'm looking for nitrogen, so moles of nitrogen has to go on the top, but the number comes from the balanced equation. Now I've got one more step, because moles of nitrogen is not what I was looking for. I'm looking for mass, which means grams of nitrogen. So now I've got one more step, just like you've converted lots before, to go from moles to grams. So now that I'm trying to get rid of moles of nitrogen is now on the bottom. I'm looking for grams of nitrogen, so that goes on the top. And this number is a molar mass. So this comes from my periodic table. Since I had more than one nitrogen, I had to look up nitrogen and add the 2 up together. Now all I have to do is multiply across the top, divide across the bottom, and that gives me the 21 grams of nitrogen. Reason I wrote 21.0 rather than just 21, by the way, in case you have not noticed or remembered, significant figures. It's 3 sig figs in my question, therefore 3 sig figs in my answer. All right, take that same process, see if you can try one. How many moles of NO are formed if, here's your given, 824 grams of ammonia and oxygen are used in this reaction. So here is your unbalanced equation. You've got to balance the equation first. This, by the way, is ammonia. So balance the equation first, figure out your given and your unknown, and then do the 2-step conversion. Give it a try. So balancing the equation first, got a larger coefficient than average. Your given and your unknown. The given was the only number in the question, the 824 grams of the ammonia. It's asking you for how many moles of the NO are we going to be able to form. So moles of the NO is what you're aiming at. Then you got to think about what actual numbers you're going to need. Conversion factors you're going to need are the mass for the NH3, when we're changing from grams to moles, and you're going to need a mole ratio in there too. The way you're going to end up setting this up, always start with your given. So the 824 grams of NH3 is the first thing you would write down. In order to bridge from one substance to another, I have to have moles. So I'm going to change from grams to moles first. If I'm looking for moles, that means 1 mole of the NH3 on the top. And converting to grams means that molar mass, 17.04 grams of NH3 on the bottom. This cancels out the grams. Now that I've got moles of NH3, I can get to moles of the NO. I am now getting rid of moles of NH3, so that goes on the bottom. The number for this mole ratio part comes from the coefficient in the balanced equation. So that's where the 4 comes from. And since The NO is the substance I'm looking for. Moles of NO is what I put on the top. And again, the number that I plug in for it comes from the balanced equation. That one happens to be a 4 also. Multiply across the top, divide across the bottom, and you should get 48.4 moles of the nitrogen monoxide. Again, I had 3 sig figs in my question, so 3 sig figs in my answer. We've done a 1-step problem, we've done a 2-step problem. Now it's time for a 3-step problem where we start with grams and end with grams. Again, taking a look at the mole map to see where we're headed. Now we're going to start with grams of one substance. You'll divide by the molar mass to get moles, just like you did in the last problem. You'll go from moles of one substance to moles of another, just like the last problem. Only now we're going to add one final step, multiplying by that molar mass to go from moles to grams. So this will be just like the last problem you did, but one extra step to get it back into grams in the new substance. Take a look at an example first. We've got laughing gas, which is dinitrogen monoxide, and water produced when ammonium nitrate decomposes. We want to know how many grams of the NH4NO3 we need to get 33 grams of the N2O. While this is more steps than what you've seen before, this is actually the most useful kind of problem, because when you're dealing in a lab, you use scales, you use balances. They measure things in grams. So you got to know how many grams of one thing you weigh out to produce a certain number of grams of the product that you want. So while I realize this is definitely the most work of what you've seen so far, it's actually the one that's going to be the most useful in a setting where you can actually measure something. So first thing I'm going to do is have a balanced equation. Here's our equation. Next thing I'm going to do is identify what you're starting with and where you're ending. Only number in my question is my given here, the 33 grams of the N2O. It's asking me how many grams of the NH4NO3 I need. So grams of NH4NO3 is what I am aiming for. Then it's helpful to kind of think about what conversion factors, what numbers you're going to have to be plugging in. Since we're changing between grams and moles for both of those substances, you're going to need these molar masses from the periodic table. So these are numbers we added up all of their masses from the periodic table. And you're going to need the mole ratio from the balanced equation. So, have we plug everything in, lead you through this. Our given is what we started with, so that was the first thing we put down. Next is changing from the grams of the N2O into moles. To change from grams to moles, since I'm canceling grams, grams goes on the bottom. This number came from adding it up on the periodic table. That gets me moles of N2O. Then next is like the very first problem we did, that mole ratio step. I'm trying to cancel out the N2O now, so N2O goes on the bottom. This one comes from the coefficient in the balanced equation. Since my unknown is this NH4NO3, that is now what I'm aiming for, so that goes on the top. The number comes from the balanced equation. In this case, that happened to be a 1-to-1 ratio, but that definitely is not always the case. So we always want to plug that in there and check. Now that I've got moles of the NH4NO3, moles now goes on the bottom. And grams, because that's what I'm searching for, grams goes on the top. Gram numbers always come from your periodic table. So this 80 is coming from adding up the 2 nitrogens and the 4 hydrogens and the 3 oxygens. Once you've got all your numbers in place there, you're multiplying everything on the top, dividing everything on the bottom, and that should give you right exactly 60 grams. We left it as 60.0 because I had 3 sig figs in my question, therefore 3 sig figs in my answer. Whew. That's as long a problem as you're going to get. Let's see if you can try one exactly the same pattern. Convert grams to moles first, mole ratio step, moles back to grams. So here is your problem. I will go ahead and give you a balanced equation to get you going. So here's your balanced equation. You're going to be starting with the 100 grams of copper and figuring out how many grams of silver you're going to get. Take a couple minutes, work your way through the process. If you don't try to practice these, they won't get any easier. So please give it a try. convert grams to moles, mole ratio step, moles back to grams. 3 steps, give it a shot. So here's your given and your unknown. You were starting with that 100 grams of copper, trying to figure out the grams of silver. Things you're going to be needing are that mole ratio and masses for silver and copper from your periodic table. Here's what your final answer should look like, but let's take a look at the setup. You've got 100 grams of the copper. First thing you do is convert the grams into moles. So 1 mole of copper, and then its molar mass is about 63.5 grams. Goes on the bottom. That gets rid of my grams of copper. Next is that mole ratio step. I got to bridge from the copper to the silver. So now that I'm trying to get rid of copper, moles of copper goes on the bottom. I look at my coefficient here. No coefficient means I plug in a 1. I'm looking for silver now. Silver is what I'm trying to convert into. So moles of silver goes on the top. Coefficient in the balanced equation is what I plug in for moles here. Now I've got the moles of copper canceled out. Since my unknown asked for mass, I have one last step, and that's to go from moles to grams. So since I am now canceling moles, I put 1 mole on the bottom. I'm looking for grams, so grams of silver goes on the top. The number comes from the mass on my periodic table, which is about 107.7. Multiply all the numbers across the top, divide all the numbers across the bottom, and that's where I get this 339 grams. Again, 3 sig figs in my question, so I only get 3 sig figs in my answer, 339. You can work your way through this. You're in fabulous shape. One more thing we'll add in here. It's the same number of steps, but now we'll throw volume in there as a possibility instead of grams. So if you look at just 1/2 of this, this is exactly the mole map that you had before. We just didn't put atoms or particles on there. So you can now convert really between all of these different substances just following your pattern here. What we've done at this point is go from grams to moles, moles to new substance, moles back to grams for the new substance. We can also throw volume in that mix, provided we're talking about gases at standard temperature and pressure. Remember, 1 mole of a gas was equal to 22.4 liters. So I could also go from the volume of a gas, figure out moles, bridge to a new substance, figure out the mass. I could go from mass to moles, moles to something else, go to a volume. An even easier shortcut, one other thing I can do, because it's 22.4 liters on both sides here, if I have the volume for one gas and the volume for another, I could just use that same mole ratio and go from liters to liters in one step also. So you got a lot of different possibilities here. Let's see if we can try a volume problem. One thing I would recommend also, guys, even if you don't normally print out PowerPoints, I might print this one out, or at the very, very least, print out this slide, because this slide has a nice, good double mole map and has all the reference you need to work through all these different types of problems. So even if you don't normally print out the PowerPoints, I would at the very least print out this slide. I really do think it would be a good, helpful resource for you. So let's try an example with volume in here. I want to know how many moles of nitrogen gas I need to react with 44.8 liters of hydrogen to produce ammonia. So here is a balanced equation to get us started. Got to identify my given and my unknown. Given is whatever number I had in the question. Unknown is what the question's actually asking for, which was moles of nitrogen gas. Figure out what conversion factors I might need. Since I'm starting off with liters, I have to be able to go from liters to moles, and that's that 22.4. I'm also going to need my mole ratio to go from one substance to another. So here's what my setup would look like. Remember, my given, always the first thing I write down. I'm trying to get from liters to moles first, so 1 mole on top, 22.4 liters on the bottom. That's what cancels out liters. Then I can go from one substance to the next. This is that mole bridge part. So moles of hydrogen cancels out. The number for hydrogen comes from my balanced equation. Pardon me. I'm looking for moles of nitrogen. So moles of nitrogen on the top. Again, coefficient in the balanced equation is the number that I use. Because it asked for an answer in moles, I get to stop here. I could also have asked for it in grams, in which case you've got one more step to convert it into grams. But in this case, I asked for moles, so we get to stop at 2 steps. Multiply top, divide the bottom, gives you 0.667 moles of the nitrogen. Your turn to give it a try. How many liters of carbon dioxide do I get when 24 grams of carbon reacts? So here you got to go through all 3 steps. I will go ahead and balance the equation for you to get you started. See if you can go through the rest of it. It will be 3 steps. Got to get grams of carbon into moles, moles of carbon to moles of carbon dioxide, and then moles to liters. Give it a try. Please, please see if you can get this set up. Use your mole math if it helps you, but definitely give it a try. All right, your given was that 24 grams of carbon. The unknown, what you're searching for, is liters of CO2. Here's what your setup's going to look like. Your given is what you write down first. We're starting with the 24 grams of carbon. First thing I have to do is change grams to moles. So canceling out grams, gram numbers come from the periodic table. Now I've got moles of carbon. Going from moles of carbon to moles of CO2, here's where I'm bridging from the one substance to the other. So moles of what I'm getting rid of on the bottom. Number comes from coefficient, where is it, in the equation. Moles of what I'm looking for is on the top. Again, number comes from coefficient in the balanced equation. Now I've got moles of CO2, but the question asks for liters of CO2. So my last step is now to go from moles to liters. And my conversion factor there is 22.4 liters for every 1 mole. Multiply across the top, divide across the bottom, and I end up with exactly 22.4 liters of carbon dioxide, precisely 1 mole. Those are some very, very tough notes. I'll tell you that this is the kind of thing where practice makes perfect. Practice, practice, practice. That's why this section on your point sheet has the most worksheet options, because practice really, really will help. Please do ask me questions on anything you're stuck on. This is the kind of thing, it's not going to go away. So if it's not working for you, talk to me so I can help you out. Okay? Excellent job. Long podcast. You are all finished.